Okay, in the previous video what we had discussed was the delta network. We also had looked into the generic banyan. We also looked into how the shuffle net actually act as a delta network. Okay, we in fact gave a proof that any kind of shuffle interconnection based network will ultimately will be a digit control routing network. Digit control routing networks were the networks where you actually put the output address as a tag at the input port and packet will self route through the network and ultimately reach to the output where you want it to actually go. So, but at this point of time we should also now try to compare how the delta network works compared to a crossbar, because I can make the packet switch with both. So, let us try to see how we can actually do the performance analysis of a crossbar and delta and compare these two. After this then we will move over to the buffer delta network, how to actually model them and how to do the performance analysis, how that actually is done. So, this is a computational procedure which actually is used for doing the performance analysis of a buffer delta system. And of course, if time permit I will do some of the things which are extra just for the sake of knowledge, they will not be coming in the examination. So, throughput of the crossbar, so let us start with that. So, crossbar is of the size m by n, that is what I am assuming, it is a m by n crossbar, and remember it is a packet switch. So, what I need to find out what is going to be the throughput at the output. So, probability of arrival I am actually of the packet at the input. It is a slotted system. I am taking it as an m. So, if there is a m by n crossbar, so packets are coming at the input and it is a slotted structure. So, in one slot packet will be coming at various input ports, second slot this new set of packets will be coming in, and the probability that a packet will be there in a slot is given by m. So, that is what I have written here. And of course, again I am assuming that there is nothing like a input queuing here. So, if the packet more than one packet want to go to the same outgoing port, I will only allow one packet to go through, the second one will actually be dropped. So, all but one of the contending packets will be dropped and one will be put to the outgoing port. Okay. So, that is the assumption. So, I am assuming if the packets are contending all but one, for an output port, all but one of the contending packets will be dropped. Of course, in fact I should now change the number. First is assumption is that I am using a slotted scheme. So, time slots have been defined and in one slot only one packet will be coming and then it will be switched out. We also do assume now the fourth thing. We assume that there is no correlation between the slots. So, pure independence is the fundamental assumption which we have been making. So, when you are actually having a time series, there are multiple slots at a input. When a packet arrives here and packet arrives here, these two packets are independent, they are no way correlated. It is not that if a packet has arrived here, there is a higher chance of packet coming at this point. So, there is no correlation between them, it is purely independent event. So, that is another assumption. So, Qi which is going to be probability that I packets arrive at the input inputs of the switch. So, remaining m minus I inputs, there is no packet arrival on those. So, this probability normally will be given by m c I. M is the number of input, out of this only I inputs are going to have the packets, and this happens with the probability. M is the arrival rate, arrival probability, and with 1 minus m there is no arrival. So, this will be m minus I. So, that will be the probability, and of course, we define E of I as the expected number of packets which are through to the outgoing port. Given that I packets arrived. So, to determine this value of EI, so we go in this manner. So, if I packets are arriving, they can be directed to any one of the outgoing port with equal probability. Okay. So, in how many ways the I packets which are coming can be mapped onto these outgoing ports. So, each packet can go to any one of the n ports, there are n possibilities, and since they are I, so that the way they can be mapped onto these will be nothing but n into n, because each packet can take any one of the n outputs, n possible ways. So, these will be done I times. So, which implies n raised power I. So, I packets can be mapped to all outgoing ports in n raised power I ways. So, if I look at an output and that output is not being selected, in what all ways actually that can happen, which actually means these I inputs are now being mapping onto these remaining n minus 1 outgoing ports, and this will happen in how many ways. So, in n minus 1 ways, one packet can choose these. So, there are I packets, which implies n minus 1 raised power I ways, the mapping can happen from these I packets to these n minus 1. So, this implies that n raised power I minus n minus 1 raised power I are the number of ways in which these are the number of patterns where this output, specific output will always be there. A packet will at least be mapped to this, one packet at least will be mapped to this. So, these are those many number of ways. So, total number of ways in which the mapping can happen is n raised power I. So, this should be the probability that an output will be selected. Okay, this will be the probability that output will be selected, and that is what is also the expected number of packets which are through, given that I packets are arrived. So, this is a probability that at least one packet will be coming out here. There are total n number of ports. So, this must be raised power n will give me EI. Okay. So, I can actually now use this to compute the throughput. So, throughput is summation of when I can go from 0 to m. So, minimum 0 packet can come in and maximum number of m, which can arrive in a time slot this expected packet which will be successfully passing through to the output, and probability that you are going to have I packets arriving. So, we need to solve this. So, this turns out to be summation of. So, I can actually solve this one, I can take n raised power I out and then make a solution. So, this will be 1 minus one over n raised power I into n. So, this n raised power I, these once you put, you will get 1, this can go inside. So, 1 minus 1 over n, that is what is there, total power I, which will be there, right, and this is the n. So, this total is E I, and then of course, I put in the value of Q I, which is m C I m raised power I 1 minus. So, this is what is going to be the throughput. So, this now can be written as, with this one so n will be, this n I can take out, m C I minus so I can expand this. So, this value is nothing but m plus 1 minus m raised power m, which will be 1. So, I can multiply it by 1 minus. So, again this will be this plus this entity raised power m. So, this m cancels. So, you will have n minus n so that is what will be your throughput for m by n crossbar. So, fractional throughput, if you want to estimate, you can actually get it. So, fractional throughput will be so fraction of whatever is coming at the input, how much of that is going out, that is a fractional throughput. This now can be estimated as successful packets divided by total arrived packets at the input. Remember, the packets which are not in the contention, which are not successful, they are being dropped out. Okay. So, that is why a fraction of the whatever is the incoming number of packets only is going out, that is a fractional thing. So, this will turn out to be whatever is the throughput which we have, that is the total number of packets which are going out will be n minus n 1 minus m by n raised power m divided by total number of packets which are coming is m into m. Okay. So, this value will be n by m n minus n by m n sorry n m So, when m and n is a basically symmetric square crossbar, then n will be equal to m, and then correspondingly things will change there. So, this will be 1 minus so you can I can always simplify this thing to figure out the fractional throughput as for a very large values. So, I can write m is equal to k of n. So, this ratio is fixed, and then I can take n goes to infinity and then actually solve for this expression. So, I will get this thing is one over m k minus 1 over m k So, I can define this as m by n So, this particular part is going to change when I am going to take n goes to infinity. So, I can write this thing as 1 minus m by n raised power n by m minus km. So, in fact, we can see this particular fact will be nothing but when n goes to infinity, this will get converted to e. So, this whole thing will now be e raised power minus m k. So, when n goes to infinity, this what you will get is m k minus 1 over m k 1 minus this will be e raised power minus m k, that is what will be your expression for the fractional throughput. Okay. So, that will be the fractional throughput. So, in fact, we can write it as 1 over m k 1 minus e raised power minus m k. So, m is the probability which goes from 0 to 1, and we can see as m actually grows, when this is 0, this value will be 0. When m actually grows, this will actually take a maximum, then again it will drop. Okay. It will in fact when this is infinite, this will go to 0. So, 1 over m k. So, this technically goes from, it will saturate, and this value will be 1 over m k on saturation. Okay. So, that will be the maximum throughput which you can have, and k will be 1 when m is equal to n. So, 1 over m will be the maximum throughput which is possible. Now, let us look at the delta network. Okay, this value when m is growing, m can take maximum value of 1. So, when m will be equal to 1 and k is equal to 1, you will get maximum value as 1 over 1 minus 1 over e. That is the maximum value which you can get as a throughput as you are increasing your m for a very large size switch, and this will be for k is equal to 1. When k is not equal to 1, the value will change correspondingly. So, now look at the delta network, how you will find out the similar kind of throughput performance for a delta network. So, once you have this, you can actually compute. For delta network, you have to do a computation to find out that ultimately the throughput. Okay. So, let us see how that can be done, and then you can do a recursive computation and find out the throughput, and once you plot how they compare with each other. So, let the delta network will be of size a raised power n by b raised power n, I am considering that, and then this is basically going to be built using a by b switches, multiple of them. So, there will be total n stages, and each one will consist of a by b switches. So, we can take the crossbar result for a by b. So, a by b is a crossbar. So, the output arrival rate at the input is m of a by b, So, m is the arrival rate here. So, what is the outgoing rate that we need to compute? So, this will turn out to be nothing but, we can actually use the same similar computation which we did. This will be B minus by this. So, what does it mean is, when a packet is going to come, this comes with m, probability m, this is going to be directed to one of the B's things. So, the probability that a packet is arriving here for this outgoing port is m by B. Okay. So, the probability that a packet is not going to arrive at this port for this one is 1 over 1 minus m by B. So, that is a probability no packet will be coming here. Okay. This does not happen in any one of the incoming port, that probability will be A. Okay. So, and then of course, 1 minus of this means there is going to be at least one packet coming for this outgoing port. So, that will be the throughput, that is the probability that a packet will be available here. Okay. So, the overall throughput will be, if I consider all these B ports, so I simply multiply it by B. So, that will give me the total throughput at this outgoing port, and that is what this throughput is all about. So, the probability that packet will be here, so I call it, if this is the jth switch, is this one particular switch. So, if I call it m in, so m out will be given by this expression. So, I can write down m of out is 1 minus m in by B raised power A. Okay. So, once I have this, what I can do is I can do a recursive calculation. So, we will do actually certain theorems and lemmas here which will justify this argument, this basically comes from there. So, if I know the input, I call it m0, I can find out what is m1. Okay. So, remember that each one of the input packets are, each one of the inputs are coming, the packets which are coming, they are coming independently. So, these packets, since it is a uniform distribution, uniform probability packet is going out anywhere. So, I can find out m1, this m1 should be same for all outgoing ports after the first stage. So, all packets, since the input here in the next stage is going to be connecting, having a path only from certain thing, certain inputs, and this size of the inputs are going to be same. So, the probability of arrival is going to be same here. So, this premise can hold recursively, and I can find out from m0 to m1, m1 to m2, ultimately I can find out what is going to be m of n minus 1. Okay, they are total m of n, sorry, m of n, this is the nth stage, this is the first, second, nth stage. Once I know mn, so that is a probability that a packet will be available here, and since total number of outgoing port will be B raised power n, so throughput should be m raised power n into B raised power n, mn into B raised power n, that is a total throughput. And of course, the relative throughput will now be, if I know the input total number of incoming ports is A raised power n, and we had a packets coming with m0, okay, or we call it m actually here. So, this will be the relative throughput. So, this is the basically number of fraction of incoming packets which are being pushed out as a function of m0. So, but this has to be done computationally. Okay. So, now we can actually compare this relative throughput. So, if you compute and plot, so I can just plot it for you. These are relative throughput for a crossbar as well as for delta. So, how they compare? So, computationally the graph will look something like this. So, it will start from 1.0, this is probability is there, you start with 1, then 2, then 4, 16, 64, 256, 1024, 4096. This will roughly saturate at about 0.5, 6, 7, 8, 9. So, roughly this will be, it will start saturating here, this will be the crossbar. Okay. We can also build delta 2, delta 4, basically it depends on whether I am going to build it by 2 by 2 elements or I am going to build it by 4 by 4. So, if you take delta 2, this will be something like this, and if it is delta 4, it will be something like this. So, crossbar is always going to give you the best performance, but of course you need more central CPU which is going to do the header processing, that need to have higher capacity to process the more number of headers. You actually do a distributed computation here, you do not require a centralized CPU, central CPU to do all the computation. You can just put the tags at the input, self routing is going to happen, you can build larger switches. So, that independence is at the expense of your relative throughput. So, relative throughput dies away, but you get more independence and more resilient system. Even if few switches, some CPU fails, still part of the switch will keep on functioning. Okay. So, that is, and of course crossbar is fully strictly non-blocking network, but this one are the blocking networks. Okay. So, in fact if you want to estimate permutations between a crossbar and delta, I think I can do that. So, if you have a crossbar of n by n, so how many possible connection patterns which can exist? So, one input can get connected to n of them, the second one can connect to remaining n of them, n minus 1. So, it will be n into n minus 1 into n minus 2 till 1. So, this will be n factorial. So, n factorial ways the basically connection patterns are being supported by this. While if you look at the delta network, delta 2 for example, and if it is n is equal to 2 raised power small n, with that capability, this actually means with 2 by 2 you are going to have n stages, okay, and each switch will have, you will have n by 2 switches. Total number of switches will be actually n by 2 into log 2n, and each switch can actually have two states, either cross or bar. So, total number of possibilities will be 2 raised power n by 2 into log 2n. Now, this number, these are total number of permutations or combinations for any Banyan network. It is not only delta, for any Banyan network these are the possible permutations, input to output maps which can be handled. This number is far smaller than this number is much larger actually, okay. So, n factorial is much larger than this, and because of which the blocking will happen and you will have a poorer performance, okay, because we remember we have assumed the contending packets will be dropped. As I go from delta 2 to delta 4, delta 8, this will tend to become as good as a crossbar, okay. So, crossbar actually saturates at this. So, if you keep on increasing your delta size, the output B number, delta B, the B goes from 2, 4, 8, 16, it will tend to become equal to crossbar. So, that is how the crossbar vis-a-vis delta network performance actually can be compared.